So this is a professional education segment provided to the North Country Stormwater Conference in fall of 2021. And we pick up the conversation talking about the North Atlantic Aquatic Connectivity Collaborative, or NAC, and the use of the NAC data model for collecting and archiving culvert inventory information. So I wanted to walk you through an example download I did for the town of Essex. And I picked it at random just so we can talk about the different outputs a little bit. So we have these GIS shape files and Excel reports down here at the bottom. And the thing I want to point out is the difference. So this is the Excel file. So the difference between the survey ID, which is for the crossing, and the NAC culvert ID, which is to each individual culvert. So it's important to know this as a modeler, whether we're modeling culverts or whether we're modeling crossings. So note that you can have no culvert ID where there is no culvert at the crossing. You can also have duplicate survey IDs where there are multiple culverts at each crossing. So NAC actually makes it easy when you download the Excel file, highlights in purple the crossings where there's more than one culvert. Now, in the town of Essex, the detailed Excel report, we end up with 96 rows. So we have to strip out the header, you notice in the green, if we want to actually use the data. So we end up with 88 crossings, right, which translates then also into 66 culverts. So unique NAC IDs. So when we compare this to, say, the GIS file that we download, what you get is, in this case, you also get 88 crossings, which is not always the case, surprisingly. But you get a different set of columns or attributes in here. You don't actually get culvert data, you just get crossing data. And they don't all appear to be in the town of Essex. So one of the things I want to point out to you is that it's not NAC's job to clean the data, right? So the data could meet the data model requirements to be input into the NAC, but it could still have some nuances and things that that need to get resolved during QA/QC. So one of those, a lot of the data is manually entered, right? So the manual data entry for the town code or the county code or the watershed code needs to be checked to make sure that it's correct. And that's may or may not align with the GPS coordinates like we're showing on here. So we can actually import the Excel file and use the GPS X and Y coordinates. And we can use the GIS file with its X and Y locations, and we can compare them. And so for the most part, it looks really good. And in both cases, I used the GPS locations that were measured in the field. And the two main points is that I want to sort of talk about here is that this is not unique to the town of Essex at all. Like I said, I just picked this up completely at random. It happens all the time. So we're going to shift in a minute and talk about modeling next, right? So the purpose of modeling is to use this data to calculate the capacity of these crossings and to estimate the peak flows that come into them and see where there might be things that are undersized or at risk. So before we move to modeling, just a quick review. So what are some of the three key elements of a NAC field assessment? Right. Well, we need to get the geometry of the culvert itself, right? Material type for roughness coefficients and that sort of thing, and condition. And then one of the unique things that comes with NAC as an aquatic assessment is this thing about biological passage, which is a pretty important part of the NAC assessment. But what are three key data quality elements once we put that data into the NAC database? Well, as we've seen, the GPS locations need to be QC'd. The manually entered fields that are relevant to the location or the information above need to be QC'd. And we just need to understand clearly whether we're talking about crossings or whether we're talking about individual culverts. So now everyone gets to take a deep breath because I'm going to probably go really fast through the rest of this, but you can always rewind and review this and come back later. So we don't really only have to worry about three things when it comes to doing this sort of culvert capacity and peak flow modeling. So I've already started to give you a sense of that with the NAC data. But ultimately, if you get one takeaway from this segment, it's all about preparing the data and getting the input data right. So my main point is that the input data affects the results. Now, if you change the inputs, that changes the results. I mean, it seems obvious, but to me, that means we need to be super careful about getting the data right before we start getting too wrapped up in what the model is actually doing. So here are some examples of how the elevation data might affect the hydrology. So here's a suburban area, and you can see all the houses and the driveways. And here's the LiDAR data that is associated with that same spot. So the LiDAR data is awesome. I mean, it actually shows flow going down either side of the street in the curb and the gutter. And this is standard QL2 LiDAR data that we have for much of New York now. This is not anything that's a super uplift from a standard LiDAR collection. But sometimes we get these weird things we call artifacts, but they're sinks. And this is where, because the LiDAR data is so detailed, where the flow will actually go and will stop. And you can kind of see here on the imagery, this is related to, a lot of times it's related to building removal in order to get a bare earth surface, or vegetation removal in order to get a good ground surface. So what do we do about that? Well, we have to fill them in. So we fill them in so that the flow can continue down in our artificial flow network so that we can start to model this surface a little bit better. Here's another example of how sinks the existence of sinks will affect the drainage areas. So these areas in white, because there's sinks there, it won't get accounted for in our runoff calculations or our drainage area calculations. So if we fill them in, then we can connect them to the drainage network. But filling in sinks, while it's a pretty standard GIS 101 kind of activity on a digital elevation model, it has its drawbacks. So particularly, like, here's an example where we have a road with a ditch, right? So the ditch on the north side of the road, and we filled it in, but sometimes filling in sinks then overfills areas. And so we have a situation where water is now in our digital elevation model spilling over the road where it's not supposed to because we filled it in. So what to do? Well, we use brake lines to then fix that problem. So we can add brake lines along the road, see in purple, and force the flow to go down the ditch line to the culvert on the right. So here's another example where, we know we have flow on either side of the road, and at the bottom of the screen, it's actually doing pretty well, but at some point it kind of gets a little wonky. And so if we put in some brake lines, we can actually enforce the flow on either side of the road where we know it's supposed to go. Here's a situation where filling has caused the flow to go over the road in two different places. And it really should only be in one place where the culvert is. So we can either add a brake line and force the flow on the right to go down into the culvert, or we can just move the point a little bit and we get essentially the same result. And sometimes we also find that the GPS coordinates for where the culvert is aren't exactly right. So we make some administrative location adjustments just for modeling purposes so we can either put brake lines in or we can shift the points a little bit just to get them in the right spot so that we can begin to do our modeling. Here's an example of a GPS coordinate on a culvert where we're not really sure what to do. Right? So where do we move it? We can see the stream kind of on the north side, but we have drainage on the south side where there's probably a culvert to the left, there's a culvert to the right, and there's a culvert kind of to the north and to the right. So these are some things that this is a valid NAC record. It will be entered into NAC. NAC will accept this record, but we need to make sure through a separate QC process after the fact, when we pull records out of NAC, that they're actually where we want them to be and that the information in the tables is actually accurate. So we talk about doing this editing process of adjusting the DEM, adding brake lines, moving the points around, but how much editing do we really need to do? So here's an example. You can see there's a big watershed here in purple. We have county culverts in the upper right-hand corner. There's like 3 blue squares up there that represent county culverts. And so this is probably a fairly accurate representation of the drainage area to these county culverts. But if we wanted to add town culverts into the mix, now we have a lot more culverts. So there's a lot more to check. And so the question is, how much do? We edit at the scale of the analysis we want to do. So in this case, we need to go into these town level culverts and check. And then we only really need to edit where it matters. So here's an example where you can see a number of culverts in blue, and you see these red circles indicating where the flow field is indicating that water is flowing across the road. So what's going on here? Either we've filled in a ditch artificially and are spilling water over the road, or we have a culvert missing in our inventory. But regardless, we only need to make an edit here if it changes the end result. And in both cases here, the result is the same, so we don't need to make an edit. So this is sort of an engineering analysis and a judgment call on where we need to make edits to get the drainage areas correct. So now we can get started with the modeling. So we've identified data issues, you fix what you can, and whatever you can't fix, you just flag so that at least you're aware as you move forward what you may have left behind. So I want to talk for a few minutes about the model that we use with the Hudson River Estuary Program. And it's a model that has come out of the Department of Biological and Environmental Engineering at Cornell. And one of the key takeaways, as I mentioned before, is that the inputs, whether it's this model or any other model, right, the inputs have a huge impact on the outputs. So here's a graphical representation of what the Cornell culvert model does. Don't get too wrapped up in each box, but essentially each box represents different steps that either use Python scripts or an ArcGIS process to calculate different things. So this one route gets you through the model to estimate runoff and peak flow at each crossing. And this other route gets you through estimating the capacity of each culvert. And then ultimately down here is where we want to compare the capacity of the culverts at the crossing with the amount of water that we're anticipating coming in as a peak flow. So one of the cool things is that it's GIS based. Now, this is not a hydrology class, but in order to solve the hydrology equations, we need something, in this case, we need something called a curve number, right? So that's essentially a runoff coefficient that handles infiltration. So that comes from land cover and soil type. So there are tables in TR55 in the documentation for estimating this curve number. But the folks at Cornell did a really nice crosswalk with the national land cover data and soils to get a standard curve number layer across the Northeast region from Pennsylvania to Maine. So we have that as a GIS input layer. And when we do these calculations using the GIS, it's important to understand that the first thing that really comes out of that is this Q, right? What's the volume of water that we can expect to come out of this watershed, out of this catchment area for a particular storm event. So we need a way to then translate this volume of water that came out of the sky and is moving across the landscape. We need a way to translate that volume of water into a peak flow based on the characteristics of the watershed. So for that requires our elevation model to calculate slope and distance and travel time. And that way we understand what the rainfall has to do before it arrives at the front end of our culvert. So here's a super simplistic way to look at that. This is a peak discharge hydrograph. It relies on something called the time of concentration. Right? So what we're calculating here is the time of concentration that it will take for the total volume of water to pass downstream to get to where the peak flow is at our culvert. So these figures and these equations and this documentation comes from the Cornell culvert model documentation. And one of the things that I also want you to take away from this is that there's lots of ways to calculate these things, right? There's not, that was a super simplistic hydrograph and a super simplistic way of calculating time of concentration to understand the concept. So we have an equation that we can apply. We run that into a Python script, or we can even code it directly into an ArcMap project. But the Soil and Water Conservation Service has a lot of different methods and a lot of different equations that can be used. So engineering manuals have a lot of different methods and equations. So the Cornell culvert model uses just one, and it's one a fairly simplistic but rapid way of getting at this problem of concentration. So ultimately, then, this is what the GIS calculates, right? So the GIS will calculate for any given culvert or any given crossing. It'll calculate the drainage area, the average slope, the maximum flow path that water would have to take down that drainage area to get to the culvert, and the average curve number for infiltration purposes. And then the only thing we need to then do is throw some precipitation at it, and we can start to calculate volumes and peak flows. So speaking of precipitation, here's a standard table. This is downloaded from the NOAA, the National Weather Service, the Atlas 14 tables, for those of you who are familiar. And it's a precipitation frequency estimate. So we can start to look at the 1 year, the 5 year, the 10 year, and the 50-year estimates as we move across the table. So if we zoom in, say, to use the 10-year, 24-hour storm, then in the Cornell culvert model was sort of built around the concept of the 24-hour storm. But we can use anything on this table. And as you can see, our understanding of what a particular rainfall event might be that happens outside, either last week or last month, and comparing that to a precipitation frequency estimate is kind of an important thing, because we can change the precipitation estimates based on these frequencies. And of course, we're going to get a different answer in terms of our modeling. So then, this is what the model looks like in terms of its output. It's just a bunch of tabular data that's aligned with each culvert. And then that kind of brings us to the big question, right? So, how accurate are these model results, right? How well do the model results compare when we observe, when we compare them to what we observe in the field? And to me, that's really not the point. I think, to me, the point is less about calibrating the model to match field observations than it is for the modeling effort to be consistent, so that you can compare results from one culvert to the next, right? And you can compare peak flows from one location to the next. You can spend a lot of time and money trying to calibrate something. But as I said earlier before, if you just change the input slightly, or use a different calculation method, or change your precipitation, you're going to get a different result anyway. So here's an example from the Pennsylvania DOT that it just sort of illustrates the range of different methods that are available to use just on the hydrology side, trying to understand peak flows. And every one of these methods is going to give you a different result. Here's just some example data. We did a project for Ulster County here in New York, just to try to understand better what happens in this exact same model if you just change out the elevation model from a standard 10-meter USGS DEM, which are ubiquitously available and easy to download. Actually, the basis for what the StreamStats program is built on, for those of you who are familiar with StreamStats, versus a high-resolution LiDAR DEM. So, and one of the things we notice is that it's a big difference, right? Just changing out the DEM has a significant impact on the results. So that's all hydrology, right? Trying to understand flow across the landscape to get at peak flows. Now, let's talk just a little bit about hydraulics, which is trying to get at this idea of the capacity of each culvert. So the Cornell culvert model looks at just one of these approaches. But as you can see, so that we collect all of this geometry data on the right during our field assessments, and we put that into the NAC data, so we can suck that directly out of the NAC data. But say on the left here, we've got 3 different inlet-outlet conditions based on whether the outlets have submerged or not, and what the headwater conditions are. And of course, each one of these different conditions has a different equation. So they're going to give you a different result in terms of the capacity of the culvert. So to try to make the model simple so that we can apply it universally, the Cornell culvert model uses the second method right in the middle, right? So there's the equation that it uses. Now, if you wanted to do something more complex, right, where you wanted to look at cross sections or do more advanced calculations on how, what is the volume at which water will spill over the road, then you're going to need a lot more data. And that's data that's not actually included in the NAC. So one of the things that we're finding is that some of our partners and some of the practitioners within the region are adding some additional data to their field assessments and their field measurements. And so we sort of call that NAC plus, right, where they have additional cross-sectional data or additional geometry data in the channel coming into the culvert. If you imagine two culverts that are exactly the same, but they have different road profiles above them and different channels coming into them, they're going to have different hydraulics. The Cornell model treats them the same, right, because they're the same size culvert. But obviously, when you're thinking about road overtopping or backwater flooding, they're going to have very different responses. So that requires cross sections, road profiles, a bunch of other information, and requires a different kind of level of modeling that may or may not be possible on a batch mode like what Cornell does. So one of the contributions that the Cornell model provides is that the inputs are standardized. They're GIS based, so they're not customized to each individual culvert, right? We standardize the inputs across the watershed or across the municipality so that we can run all the culverts at one time. And that allows us to directly compare culverts against each other and compare peak flows and capacity. So this is not a modeling exercise where we're looking at each individual culvert for site-specific design. This is kind of a planning tool that looks at all culverts sort of in batch mode. That brings me sort of to the end of the talk about modeling, and this is where I would pass the talk back over to my colleagues at the Hudson River Estuary Program to talk a little bit more about how they use the modeling results in culvert management and capital improvement planning at the municipal level.